Welcome to the second part of the video about algebraic numbers and minimal polynomials. In the last video we have found that these five numbers, radical 3, cube root of 2, zeta 5, radical 2 plus 3, and square root of 2 plus I are all algebraic numbers, which means algebraic over Q. And in fact, we did this by finding polynomials that these numbers satisfied, and these polynomials had coefficients in Q. So one question that you might ask is, are these the only polynomials with coefficients in Q that these elements satisfy? For example, is x squared minus 3 the only polynomial with coefficients in Q that radical 3 would satisfy? And the answer is no. I can definitely find some more polynomials with coefficients in Q that radical 3 is a root of. So, for example, if I take the fourth root of radical 3, then I get 9. So radical 3 is a root of x to the 4 minus 9, and that polynomial also has coefficients in Q. Another thing that I can do is I can multiply radical 3 by 2 and square this. So 2 times radical 3 squared is 2 times 3, so that's 6. So radical 3 is also a root of 2x squared minus 6. And as you see, that polynomial has also coefficients in Q. So it's not so difficult for you to figure out that you can probably actually find infinitely many polynomials with coefficients in Q that have radical 3 as their root. However, every one of these elements has a certain polynomial with coefficients in Q that has some nice properties. And that polynomial turns out to be unique, which is something that we're going to prove today. These polynomials are called minimal polynomials. So let's make a definition. So a monic polynomial, so maybe let's begin with the following. So let K be a field extension of F. And let alpha in K be algebraic over F. A monic polynomial F with coefficients in F of smallest possible degree such that F has alpha as a root, so in other words, F of alpha is 0, is called a minimal polynomial. Of alpha over F. So a few remarks here. First of all, what does monic mean? So monic, that just means the leading coefficient is equal to 1. In particular, a monic polynomial cannot be the zero polynomial. So it must have some coefficient that is non-zero, and the leading coefficient must be equal to 1. Okay, so we take an algebraic element in K, algebraic over F, and then we ask for a polynomial with leading coefficient equal to 1 that has smallest possible degree and alpha as a root. And such a polynomial we would call a minimal polynomial. And I just a few minutes ago, I said that the nice thing about the minimal polynomials is that they are actually unique. So this we will soon turn into that. But at the moment, I'm going to put a question mark here because I haven't yet proven that even with these additional assumptions, even with these additional restrictions that the polynomial be monic and that it will be the smallest possible degree, even with these additional restrictions, I don't yet know that such a polynomial would be unique. Let's look at this example here first before we move on. And immediately I see that this polynomial cannot be minimal for radical 3 because it's not monic. On the other hand, this polynomial does not have smallest possible degree because yes, it has radical 3 as a root, yes, it is monic, yes, it has coefficients in the rationals, but it's of degree 4, and I can find another polynomial which is also monic, has coefficients in the rationals, and has radical 3 as a root, but is of smaller degree than this one. So this one is not of smallest degree. So how do I know that minimal polynomials even exist? Well, you can take all the polynomials that alpha satisfies, and I know that there's at least one because alpha is algebraic over f. So I know that alpha satisfies at least one polynomial. How do I know that it satisfies a monic polynomial? Well, you see, this is just a minor nuisance because if you take a polynomial that alpha satisfies, that alpha is a root of, and it's not the zero polynomial, then I can just divide this polynomial by the leading coefficient, and I get a monic polynomial. Okay, so let me just remind you here that alpha being algebraic over f means alpha is a root of a non-zero polynomial with coefficients in f. Okay, so now we're going to prove some nice properties of these minimal polynomials. Namely, we're going to show that they're unique, and then one other property which also will be very useful for us. So I'm going to erase these now. However, we will come back to these examples. So, proposition. So let K be a field extension of F, and let alpha in K be algebraic over F. The minimal polynomial, or maybe a minimal polynomial. How about I just leave the minimal polynomial? The minimal polynomial of alpha over f is unique. So there's only one minimal polynomial. Furthermore, if g, let's actually give this minimal polynomial of alpha a name, maybe f. Furthermore, if g is another polynomial with coefficients in f, is such that g of alpha is 0, so has alpha as a root, then f divides g. So the second part tells me that if I find another polynomial which has alpha as a root, then this polynomial is divisible by the minimal polynomial. And this division holds in the ring of polynomials with coefficients in f. All right, let's prove this now. Let's prove this proposition. So first, the first part. I want to prove that the minimal polynomial of alpha over f is unique. How do you show that something is unique? Well, one way that works actually quite often is to assume that there are two such things, and then you show that they're equal. So I'm going to assume, suppose f1 and f2 are both minimal polynomials. Of alpha over f. Then I form their difference. First of all, you know the f of x is actually a ring, so I can subtract two polynomials and I get a polynomial with coefficients in f. What else do I know? And the degree, well, let's call this actually this polynomial big F. The degree of big F is certainly less, or maybe I should say this, and f is either 0 or the degree of f is strictly less than the degree of f1, which is the same as the degree of f2. Okay, well, let's digest what's in that sentence. First of all, because both of these are minimal polynomials of alpha over f, they are both of smallest possible degree, so they must be the same degree. So the two degrees are the same. Secondly, they're both monic, f1 and f2. So they both start with the same. They start with x to the n, where n is the degree, plus lower order terms. So when I subtract two such polynomials, the x to the n's subtract to 0. So I only left with lower order terms. Therefore, the degree of this f, which is the difference, must be strictly less than the degree of f1 of f2. Unless f is 0, which if you recall, we didn't assign a degree to the 0 polynomial. So I have to split this into these two cases. Moreover, what happens when I plug in alpha to f? Well, that's f1 of alpha minus f2 of alpha. But f1 is the minimal polynomial of alpha, and so is f2. So alpha is a root of f1. It's also a root of f2. So I just get 0 minus 0. So I get 0. So you see, alpha is also a root of f. Okay, you were almost there. So suppose that f isn't 0. So if f isn't 0, I now have a polynomial which is non-zero, which has alpha as a root, and it's of degree strictly smaller than the degree of the minimal polynomials. Does that give me a contradiction? Well, not right away, because I don't know that f is monic. However, because it's non-zero, it starts with some power of x. Let's say it starts with, say, am x to the m, and am isn't 0. Am is the element of the field f, so I could divide that polynomial by am, and now I get a monic polynomial of exactly the same degree as my f, and it still has alpha as a root, because dividing a polynomial by a scalar does not change the fact that the polynomial had some element as a root. So if f weren't 0, I can produce a polynomial by just dividing f by the leading coefficient, which has alpha as a root, has still coefficients in f, and its degree is the same as the degree of f, so it's less than the degree of f1 and f2. Well, the existence of such a polynomial would contradict the fact that f1 and f2 are of smallest possible degree. So if this isn't 0, dividing f by the leading term gives us a polynomial of degree smaller than degree of f1 that has alpha as a root, which contradicts the minimality. Of f1 or f2 for that matter. Okay, so that means f cannot be 0. Thus, we conclude that f is 0. So f1 is equal to f2, which now proves that the two polynomials, the two minimal polynomials, are the same polynomial. So minimal polynomials are unique. Let's now prove the second part of this proposition. So now suppose g in f of x is such that g of alpha is 0. I want to show that f divides g. So I'm using the division property here that holds in the ring of polynomials with coefficients in a field. I can write g as qf plus r with q and r polynomials with coefficients in f, and r being 0, or the degree of r being less than the degree of f. You see, what am I trying to show? I'm trying to show that f divides g. So I would like to show that r is 0. And you see that I'm going to use again the minimality of the degree, because if r isn't 0, then I have that condition, and that is going to contradict the fact that f has the smallest possible degree. Okay, but let's actually work out the details, how this works here. So what I'm going to do is I'm going to plug in alpha into this equation. First of all, if I do that, then because g of alpha is 0, I get that g of alpha is 0. But so that also means that the right-hand side must be 0. All right. But here, f is the minimal polynomial of alpha, so this is 0, as f is the minimal polynomial of alpha. In particular, right, minimal polynomial always has alpha as a root. Hence, r of alpha is 0. So what? So now I have a polynomial, r. If the polynomial isn't 0, so if r is not 0, then it has degree less than the degree of f and has alpha as a root. Again, just as in the proof of the first part, I don't know that r is monic, but if it's not 0, I can always make it monic by dividing by the leading coefficient. That does not change the degree and does not change the fact that alpha is a root. and therefore I would get a polynomial which now is monic, has degree less than the degree of f, and has alpha as a root, which would contradict the minimality of f. So I'm just going to write here, this contradicts the minimality of f. Just remember that it doesn't necessarily, it's not just r that contradicts it. You might need to divide r by the leading coefficient to get monic polynomial. All right, so r must be 0. Hence, f divides g. Okay, and this finishes the proof. This proposition has a very useful corollary. So I'm going to erase the first part of the proof here and put the corollary here, but keep the proposition on the board so we can refer to it. So corollary, any monic, so let's maybe start by saying, just as in proposition, let K be a field extension of F, and let alpha in K be algebraic over F, then any monic polynomial G in f of x, which is irreducible over f, and has alpha as a root, is the minimal polynomial. Why is this a useful corollary? You see, it's not so easy in general to find minimal polynomials. You've seen in these examples that we wrote down that we found polynomials that these algebraic elements satisfied, but how do I know these are of smallest possible degree? This corollary gives us one way to sometimes be able to say that the polynomial that we found actually is the minimal polynomial. Because if the polynomial is monic and irreducible, then we know it's the minimal polynomial. And irreducibility is something that we have talked about a lot, so you have already some experience in determining if a polynomial is or isn't irreducible. Let's prove this corollary. So let f be the minimal polynomial of alpha over f. Now I can write the minimal polynomial because by the proposition I know that minimal polynomials are unique. Let g be as in the statement. Of the corollary. So it is a monic irreducible polynomial that has alpha as a root. So by the proposition, we get that f divides g. Correct? What does the proposition tell us in the second part? That if I have a polynomial, doesn't even have to be monic, but a polynomial that has alpha as a root, then I have that f divides g. i.e., i.e. g is equal to fq for some q in f of x. Now, what do I know about this polynomial q? look, I definitely know that f is a non-unit because f is the minimal polynomial of alpha over f. So its degree is at least 1. So this is a non-unit. But g is irreducible. By assumption, g is an irreducible polynomial. And I know that I cannot write an irreducible element as a product of two non-units. So if f is a non-unit, that means that g must be a unit. So q must be a unit. So q must be a non-zero constant. These are the units in the ring of polynomials. As degree of f is at least 1 and g is irreducible. So q is a constant. Now let's see what kind of constant it can be. G is monic and f is monic. That means that g starts out with x to the n plus lower order terms, and f also starts out with x to the n plus lower order terms. So if you just compare these two sides, the left-hand side starts with x to the n, and the right-hand side starts with x to the n multiplied by q. So that tells you that q is 1. So as both f and g are monic, we get that q is 1. So f is equal to g, which is what we wanted. So let's apply it to our examples. But before I do that, let's actually work out one general fact that follows from this discussion. Namely, when it so happens that the minimal polynomial is degree 1. So fact, so let K be a field extension of F, and let alpha in K be algebraic over F. Then the degree of the minimal polynomial of alpha over F equals 1 if and only if alpha is an F. Let's prove this quickly. So there are two directions to this statement because it's an if and only if statement. So first of all, if alpha is an F, then x minus alpha is the minimal polynomial. Of alpha over F. We already discussed this direction. This is definitely the minimal polynomial because alpha is the minimal polynomial must be non-zero, so it must be at least of degree 1 here. Conversely, if f equals xa plus b is the minimal polynomial of alpha over f, right? So this is a polynomial now of degree 1. So if I have a polynomial of degree 1, that is the minimal polynomial of alpha over f, I want to show that alpha is actually an f. Well then, one thing is, of course, the minimal polynomial has to be monic, so it's just x plus a. Then f of alpha is 0, so alpha is equal to negative a. Isn't it? Okay, so let's now move to our examples. So our first example was that of radical 3. So I claim that x squared minus 3 is the minimal polynomial of radical 3 over q. Why is that? First of all, it is monic and radical 3 satisfies it. So the only question is it of smallest possible degree? Well, the only smaller possible degree would be degree 1. However, radical 3 is not an element of Q, so it cannot satisfy a degree 1 polynomial by that fact, right? That means the minimal polynomial of radical 3 over Q equals 1 if and only if radical 3 is in Q. And we know by the, I think video number 3, that 3 is a square free rational number, so radical 3 is not in Q. So clearly, as radical 3 is not in Q, the degree of minimal polynomial of radical 3 over Q must be at least 2. So it must be this. Another way to see that this is the minimal polynomial is to apply the corollary that says if I found a monic irreducible polynomial that has my element as a root, that must be the minimal polynomial. And I know x squared minus 3 is irreducible because it's a quadratic and does not have a root in Q. So a general strategy for finding minimal polynomials